The purpose of this video is to talk about ionic compound formulas. In other words, if you are given the name of an ionic compound, how do you come up with the formula for that compound? And there are a couple of considerations we'll talk about to begin with. First of all, we must realize that whenever we're talking about a compound, compounds are electrically neutral. Overall, they have no net charge. They're not positive, they're not negative. Now, with ionic compounds, we know they're made up of positive and negative ions, but overall, the compound is going to be electrically neutral. So when we write the formula for an ionic compound, we're not going to show any charges in the formula. And that's not like when we write the symbols for ions themselves, we include the charge, but not for the compounds. So here's our example, classic ionic compound, sodium chloride. We know that sodium chloride, it's an ionic compound. It contains the sodium ion and the chloride ion. And when we write the formulas for the ions, we include ion in the name. And if there's an ion in the name, we're going to include the charge in the symbol. So we show the single positive charge on the sodium and the single negative charge on the chloride. But when we go to write the formula for sodium chloride, there's no ion in the name there, so we're not going to show any charges in the formula. That ionic compound is still made up of those ions. It's not like the sodium suddenly regains its electron and the chloride loses its electron. They're still charged ions that make up that compound, but when we write the formula for them, we're not going to show those charges because they're electrically neutral. So we're going to talk through the process for writing the formulas. And the first step, when you get the name of an ionic compound, the first step is to identify what are the ions in that compound and write down their formulas. Then what we have to do is figure out how many ions of each of the elements in there. How many do we need to balance the charges in the compound? Because remember, we said compounds have to be electrically neutral. They have to have the same total number of positive and negative charges. Now, they may not have the same number of ions of each, but the total charges have to be balanced. And I'm going to go through quite a few examples later on in this video to explain that. The third thing we're going to do is, once we know how many ions of each, is we're going to rewrite the formulas for those ions, but this time we'll leave out those charge superscripts, that extra charge information. We're going to drop that, and this time, if necessary, we'll use subscripts to show how many of each of the ions are in our formula. And then most of the time, that'll be our last step. But once in a while, we're going to have some of these compounds that require us to have a polyatomic ion. They contain a polyatomic ion, and so when we write the formula, sometimes we need more than one of those polyatomic ions to balance out our charges and make our compound electrically neutral. And if that's the case, what we're going to have to do is we're going to have to write down that polyatomic ion, and if we need more than one, we're going to have to put parentheses around it and give it an extra subscript outside the parentheses to tell how many of those polyatomic ions are required. So I'm going to go through again, I'm going to go through quite a few examples here for you, and we'll start kind of simple and work our way up. Our first example, I'm going to shrink down these rules so they're going to be up there all the time. And as I'm going through this, at any time, if you want, it's a great idea to go ahead and pause the video and try to see if you can work through these steps and figure out the formula on your own. And then if you need to, then you just restart the video and see the explanation. So our first example is calcium oxide. And we say the first step is to identify and write the formulas of the ions in the compound. So we look and say, well, it's definitely an ionic compound. We have a metal there with calcium, and we've got oxygen, the oxide ion, that says we've got a metal and a nonmetal. We're expecting this to be ionic. So we'll write the ions, and the calcium ion is Ca2+. And the oxide ion is O2-. And if you're not sure how to come up with the ion formulas themselves, then go ahead and check out another video that I've got on naming ions and on ion formulas, and that may help you out with this. So we take a look at this and say, We've got our formulas now. Now we've got to figure out how many ions of each are needed to balance the charges. Well, as we look at this, the calcium has a 2 plus charge and the oxide has a 2 minus. So at the start, we want to keep this simple. It would be nice to have just one of each. And if we have just one of each, that's going to give us 2 positives and 2 negatives, and they will kind of balance each other out. Our compound will be electrically neutral. If you add the +2 plus another -2, you end up with 0. It's neutral. So we only need one of each of these ions. So we'll rewrite the formulas, and this time we're going to leave out the charge information. And because we only need one of each, we don't bother to write the subscripts, because in chemistry, if we leave out a number, it's assumed to be 1. So our next example is for magnesium bromide. Again, we have a metal and a non-metal element there. We're expecting this to be ionic. So we write the formulas of the ions, and the magnesium ion is 2 plus. The bromide ion is just a single minus. So this time, if we try to keep it simple and take just one of each, we'd have 2 positives, but only 1 negative. That doesn't add up to be neutral. That we have too many positives. So we have to bring in another negative ion into our formula here. And so if we bring in a second bromide, now that second bromide gives us a second negative charge. So now we've got 2 positive charges, we've got 2 negative charges. Electrically, we're balanced. Now, in ionic compounds, they make these crystals with just huge numbers of ions, but the ratio of the ions in that crystal is going to be, you're going to have 1 magnesium ion for every 2 bromide ions. So when we write the formula, we're going to reflect that. And again, since there's only 1 magnesium, we don't bother to write the subscript, but this time we need 2 bromide ions, so we'll put a subscript of 2 into our formula. Next example, iron 3 sulfide. Again, we take a look at it. Yeah, it's definitely an ionic compound. We've got an ion there with a Roman numeral, we've got a metal, and we got a non-metal. So the Roman numeral again tells us exactly what the charge is on this version of iron. We've got the 3 plus version. And with the sulfide, we have an S with a 2 minus. And again, if we took just one of each of these, we'd have too many positive charges here, because we have 3 positive charges represented right now and 2 negatives. So since we don't have enough, we've got too many positives, we need another negative ion to bring in. So we bring in a second sulfide ion. But now that we bring in a second sulfide ion, now we've got 4 negative charges represented here, but only 3 positive. We've got too many negatives now. So what we can do is, the only thing we can do is bring in another iron ion to try to balance things out. But now that we've got 2 iron 3 ions, they each bring a 3 positive charge. We've got 2 things that give us 3 positive. We've got 6 positive charges now, but only 4 negatives. So guess what? We've got to bring in another negative. So we bring in another sulfide ion, and now that third sulfide ion gives us 2 more negatives, and we've got a total of 6 negative charges represented. 3 times the 2 minus gives us 6 negatives. The 2 times the 3 plus gives us 6 positives. So we've now got 6 positives and 6 negatives represented here. We are balanced for our charge, and we can go ahead and write our formula to show that we need 2 of these iron 3 ions for every 3 of the sulfide ions. Next example, ammonium chloride. Well, ammonium is a polyatomic ion, and in my class you get to use a chart to look that up, and you see that it's NH4 with a single plus charge, and the chloride ion is a single minus. So we're back to a very simple ratio. It's already a single plus, it's a single minus. We only need 1 of each, and so we'll write that out as NH4Cl. Now, we've got a polyatomic ion here, and according to step 4, it says if you need more than 1 unit of a polyatomic ion, well, we only need 1 unit, so we don't have to worry about step 4. We're already done after step 3. But in our next example, we have barium hydroxide. Again, we have another polyatomic ion here. When we go through step 1 and identify and write the formulas of our ions, We have the barium ion, which is a 2 plus. And we have the hydroxide ion, which is a polyatomic ion. It's an oxygen bonded to a hydrogen, and it picks up an extra negative charge. And again, we'd like to keep it simple and have just one of each, but we've got 2 positives and only 1 negative. So again, we'll have to bring in another negative to balance that out. And if we bring in another hydroxide ion, that will give us 2 negative charges total to balance out our 2 positive that we get from our barium ion. And now I'm about to show you something that's wrong, so don't immediately write down this next one. But take a look. Our temptation here is to say, well, if we need 2 of the hydroxide, we'll just write BaOH2. Well, don't do that. That's wrong. And I'm going to explain why in a minute, and to show you why, I'm going to take that X away for a minute. So again, don't think that means that it's right, because it isn't. I'm just taking the X away. As we look at it, if I just showed you that formula, BaOH2, it would look like we had 1 barium and 1 oxygen and 2 hydrogen. But we know we had 2 hydroxides, and each one of those hydroxides gave us 2 oxygens, and right now in this formula it looks like we only have 1. So that's wrong. So what do? Well, we look up at our step 4, and it says if you need more than 1 unit of a polyatomic ion, then you've got to put a set of parentheses around the polyatomic ion and put an extra subscript outside the parentheses. So we will go ahead here and write that we've got the barium ion, and we're going to put in our hydroxide. Now it says we need to put a parentheses around around that hydroxide, and now we've got to give it an extra subscript here that say we need 2 of those. So it's basically saying give me 2 of everything that's inside the parentheses. In this case, what's inside the parentheses is our hydroxide ion. And if you do that, that's when you get the gold star. So that's the one you want right there, not that other one that says BaOH2. You want the one that says BaOH in parentheses 2. And we'll go through one more example, because sometimes it gets a little confusing when you've got all these little subscripts and parentheses and extra subscripts. It looks a little funny, but I'm going to show you one that's perfectly correct, just so you get used to seeing them. That would be for lead 4 sulfate. We have the lead 4 ion. That Roman numeral 4 again tells us it's a +4 charge on our lead. The sulfate, we look up on the chart and see that it's SO4 with a 2- charge. We can't have just 1 of each of them, because that would give us 4 positives but only 2 negatives. So we need to bring in another sulfate ion, because that way 2 sulfate ions, there are 2 negative charges for each, would give us a total of 4 negative charges to balance out the 4 positive charges we get from the lead. So now we will go ahead and write our lead. We'll write our sulfate, and since it's a polyatomic ion and we need more than 1 unit, we need to put parentheses around it, and then we need to give it an extra little subscript. And again, that extra little subscript that's outside the parentheses is basically saying give me 2 of everything that's inside. So in this case, give me 2 sulfate ions to go along with my lead ion.